Good afternoon, everyone. This is Tooran Tavangar from University of Sherbrooke, and I'm very happy to be here today. I'm going to talk about numerical simulation of concrete pipe flow during pumping process. Today's talk will be based on our recently published article on cement and concrete journal. If you want to learn more details after today's talk, you can refer to this article. Concrete pumping brings many advantages for the construction industry. For example, it helps us to put concrete in a very difficult access location of the job sites, and this feature is very important to build the tall structure. Also, it increases the quality and the accuracy of the building. However, sometimes failure can happen. For example, pipe blockage is one of the most frequent problems that may occur during pumping process. Imagine you prepare everything, but suddenly pipe block. So you need to go and fix up that point of the problem. But sometimes you need to restart from the beginning, and you can imagine how cost it may cost for the construction industry. So what I want to say is it's very important to reach a good prediction on the behavior of concrete pipe flow or to reach a good understanding on the pressure loss of concrete through pumping process. Coarser aggregates moves from the pipe wall to the pipe center. So a very thin layer of fine aggregate formed close to the pipe wall. This layer is called lubrication layer. Lubrication layer has a different rheological properties including yield stress and viscosity compared to the rest of the concrete. This layer actually has a significant effect on the pressure loss of the concrete. The rheological properties of this layer should be known in order to reach a better prediction on the concrete pipe flow. In order to understand the rheological properties of lubrication layer or to understand the effect of this layer on the pressure loss, or in other words, in order to reach a trouble-free pumping circuit, it's very important to use numerical simulation because experimental methods had some limitation. And for us, we focus on usage of the numerical simulation to reach the better prediction on behavior of concrete pipe flow, including the migration of the aggregate through the cross section of the pipe, and also we use the numerical simulation to investigate the effect of different parameters on the concrete pipe flow behavior. Actually, we use numerical simulation to answer some important questions. We use numerical simulation to answer what is the pressure loss of the concrete pipe flow, or how we can reach a more accurate prediction on the effect of rheological properties of the concrete and lubrication layer on the behavior of the concrete pipe flow. What is the effect of particle size distribution, particle concentration on the formation of lubrication layer? And in the final step, we use numerical simulation to model the shear-induced particle migration, which is an important phenomenon in formation of lubrication layer. Objectives of this project is to simulate the heterogeneous behavior of concrete mixture with a different particle size distribution and particle concentration, simulate the shear-induced particle migration, which is an important phenomenon in the formation of lubrication layer, and also reach a better prediction or more accurate prediction on the properties of lubrication layer in terms of yield stress and viscosity. In other words, we specifically focus on the coupling effect of fluid phase of the concrete and solid phase of the concrete at the same time. We want to know what is the effect of mortar phase, aggregate phase, the different properties of the aggregate, such as aggregate concentration, particle size distribution, as well as the rheological properties of the mortar phase on the behavior of concrete pipe flow. In order to reach these specific objectives, we consider concrete mixtures with different particle size from 1 to 17 millimeter, having different particle concentration, including low, medium, and high particle concentration, which are 10, 25, and 40 percentages. And also, we consider concrete mixtures with a fine, medium, and coarse particle size distribution. Therefore, in total, we have 9 different concrete mixtures. For example, as you can see, the first three mixtures have 10% concentration, but with different particle size distribution, including fine, medium, and coarse. And for example, the last third concrete mixtures have 40 percentage of concentration, but the various particle size distribution, fine, medium, and coarse particle uh, size distribution. So in general, we have 9 various concrete mixture. Also, in order to investigate the effect of mortar phase and aggregate phase at the same time on the behavior of concrete pipe below, we need to solve Navier-Stokes equations for the fluid phase or mortar phase, and also at the same time we need to solve Newton's second laws for the solid phase or aggregate phase. We use computational fluid dynamics to solve Navier-Stokes equation. We use discrete element method to solve Newton's second laws, which can help us to predict the aggregate's motion. But in order to solve these two different equations at the same time, we need to couple CFD with the discrete element method together. To model the interaction between two aggregates, we consider 4 different types of motions, including normal, sliding, twisting, and rolling. It means that 2 different aggregates can contact each other through the normal direction or sliding direction, and also they can twist relative to each other or roll relative to each other. In order to model these 4 different type of interaction, we use a spring dashboard slider contact model. This model was proposed in 1979. Here you can see the discrete element method algorithm, which was used to solve the Newton's second law equation as well as the Navier-Stokes equation. We have 3 different time steps, including fluid time step, particle time step, and collision time step. Actually, this is very challenging in the modeling of the concrete because we have different lengths and time scales. For example, we start with the fluid time step, which is the largest time step. Then we divided this time step into the particle time step. We investigate if 2 particles collide each other or not. If collision happens, then we decrease the particle time step into the collision time step, and we calculate the contact force between two aggregates. After that, we updated the location of the particles based on the forces from the fluid or the other particles. And now I will show you the results obtained using discrete element method. Before going to the details of the results, I wanted to let you know that we model the concrete mixtures with different particle size distribution, particle concentration in a pipe. We divided the cross section of the pipe into different zones, as you can see on the left side of the slide. The closest zone to the pipe wall is called zone 4, and we show it with the red color. The closest zone to the pipe center is called zone 1, and we show it with the blue colors. We evaluated the particle concentration with different sizes in each zones, and also here the lubrication layer corresponded to the zone 4, and the bulk concrete corresponded to the zone 1, 2, up to 3. So we calculate the particle concentration in each zone, and according to that concentration, we predicted the rheological properties of lubrication layer and bulk concrete. Here you can see the evolution of the particle concentration in different zones over the simulation time. On the left side of the slide, you can see that in the zone 4, which is the red line, the particle concentration decreases over the simulation time. And in zone 1, which is the closest zone to the pipe center, the particle concentration increases. Also, on the right side of the slide, you can see that the mean diameter of the particle decreases in the zone 4 or in the lubrication layer, and the diameter in the zone 1 and zone 2 increases. Or in other words, the larger particles move to the zone 1 and zone 2, and the smaller particle move to the zone 4 or lubrication layer. For all 9 different concrete mixtures, these figures were shown here. As you can see, for the lower concentration mixtures, which is 10% concentration, as we expected, the particle concentration in the zone 4, which is the red line, decreases over the time, and the particle concentration increases in zone 1 or the blue line. It means that the coarser particles move to the pipe center. However, when we increase the concentration from 10 to 25 and 40 percentage, just it means that when you comes from top to the bottom of the slide, you can see that the highest particle concentration occurs in the zone 3, while we expected that the maximum concentration happens in the zone 1, which is the blue line. But we didn't see these kind of results for the medium and high concentration mixtures. Here you can see in more details about what I said in the previous slide. Actually, here you see that the evolution of particle concentration for the highest concrete mixtures, which is 40% concentration. As you can see, over the time, the highest particle concentration happens in zone 3, which is not what we expected from the shear-induced particle migration in the pipe, because as we know, according to the shear-induced particle migration, coarser aggregates move to the pipe center. So we should have the highest particle concentration in the zone 1 or the closest zone to the pipe center. So what is the solution? We thought maybe we can reach more accurate results by developing the code, especially in the case of computational fluid dynamics and the coupling term between discrete element method and computational fluid dynamics, because the concentration term in Navier-Stokes equation is the coupling term, and this term can cause some noisy results. We applied a smoothing algorithm to reduce the noise of the result to see if it can help us to reach a better prediction on the behavior of concrete mixtures, specifically in the case of high concentrations such as 40% concentration. We applied the developed computational fluid dynamics and discrete element method. We coupled these two methods together, and we modeled the concrete mixtures with a high concentration, 40% concentration, 10% concentration, and 25% concentration in a pipe below for different Reynolds number, including 100 and 500. And as you can see, or as we expected, for all concrete mixtures and as well as the 40% concentration, the highest particle concentration happens in the zone 1 or the zone close to the pipe wall, which actually what we expected from typical shear-induced particle migration. What I want to say is that with the developed CFD-DEM method, we can successfully predict the shear-induced particle migration in concrete mixtures with different particle size distribution and particle concentration. In this slide, you can see the motion of aggregates for different concrete mixtures through the pipeline. For example, on the left side of the slide, you can see the motion of the aggregate for the mixtures with 10% particle concentration and fine particle size distribution. And at the middle part of the slide, you can see the motion of the aggregate through the pipeline for the concrete mixtures with 25% of particle concentration. We use computational fluid dynamic and discrete element method to model the shear-induced particle migration. And the shear-induced particle migration is a very important phenomenon which can lead to the formation of lubrication layer. As I explained in the beginning of this presentation, the lubrication layer actually is very thin layer of fine aggregate which is formed close to the pipe wall. We investigated the thickness of this layer for these different concrete mixtures at the end of simulation time. For example, as you can see, the thickness of lubrication layer can vary from 3.3 to 1.5 or 1.7 depending on the particle size distribution and particle concentration of the concrete mixture. Overall, we use the numerical methodology. We use computational fluid dynamic discrete element method for the concrete mixtures, which has a spherical aggregates with a different particle size distribution and particle concentration to predict shear-induced particle migration. We can successfully predict the formation of lubrication layer and the effect of the rheological properties of fluid phase on the pressure loss or on the behavior of the concrete through the pumping process. But there are many other parameters that need to be studied. For example, it's very important to study the effect of particle shape on the formation of lubrication layer or on the heterogeneous behavior of the concrete mixture. And also, it's very interesting to investigate the effect of pipe geometry or to investigate the shear-induced particle migration or lubrication layer formation for various pipe geometry. And at the end, this numerical methodology can be coupled with the AI algorithm to reach a more optimized or more cost-effective numerical approach, which can help us to predict the complicated behavior of concrete mixtures through the pipeline. At the end, I want to say thanks to everyone who attended to this talk and everyone who allows me to participate as a speaker here. And thank you so much. And I would be more than happy if I can answer your questions. Thank you.